Okay, hi all, and I'm glad to welcome you on our JaCoV webinars. And my name is Evgeny. I'm one of the drivers of JaCoV, and I hope today's webinar will be interesting and useful for you. Actually, I also face it with some kind of problem that will be described by our speaker later. And I guess, yes, it will be really relevant for you as well. By the way, I'll ask you to type something in chat that I understand that I'm not alone here. Maybe some hi message or some pluses. Okay, and while I'm waiting your pluses, let's proceed. And I also would like to tell something about some information about our community and remind you that there inside this description, inside this stream, you also can find some reference to our feedback form. And if you spend some time to fill this feedback, it also will be really useful for you. Yeah, I see the hello world. Yeah, some pluses. Thank you for that. Yes. Feedback form and also information about email to submit your talk if you like. Yes, and of course we will help you to prepare if you really interested to share something, some your experience. And yeah, and finally there are also some reference to our Telegram chat and Community Z platform, Community Z page. It also can be some communication channel and some news you can find also there. Okay, I'm going to add our speaker Kiryl and introduce him. Hi Kiryl, do you hear me
Hello,
well?
guys. Hi, yes, I can. Can you hear me well?
Yes, great.
Great.
Okay, Kiryl, can you say a couple of words? What will be about your presentation? What topic are you going to cover?
Yeah, sure. My topic is called Spring Boot, Where Did My Memory Go? If briefly, it will cover some topics around Java memory usage in Java itself, uh, how much memory typical Spring Boot application needs, and which factors in regular projects might affect memory usage by such kind of applications. So that is main.
Okay, thanks. Sounds really promising and interesting. Okay, I guess we are ready to start, and I'll also share your screen.
Mhm.
I'll add it to stream. Yes, okay.
Okay, thank you. So
Please,
just Mhm.
the stage is yours. Please proceed.
Okay, thank you. So yeah, let me start from my presentation and let me open first slide. Okay, so a couple of words about myself. Actually, my name is Kiryl Klachkou. I am a lead engineer at EPAM Systems. For now, I have about 9 years in software development, especially in Java domain and technologies which are related to Java. I have during my path, I have some experience in project coordination and delivery management. However, my main activity for now, I would say, would be lead software engineer. Um, yeah, and maybe last 4 or 5 years, I've been working on projects with microservices architecture, so have some practical hands-on experience in this area. Okay, let's proceed. So a couple of words about why we're here and what we're going to do in this presentation, this specific one. So actually the reason why I decided to prepare this talk and this presentation in general is a real case on our production on one of the projects I worked on. Actually, on this project, we started noticing that one service type, we had microservices architecture on this project, and one of the services started catching out of memory error. And actually, as a quick solution to unblock our customers, we decided simply to increase hardware memory setting just as a quick solution. And in the meantime, we started figuring out what is the actual reason and how this problem could be fixed in a proper way. And actually, as I said, my intention is to share this knowledge to wider audience. Maybe it would be useful for someone else. Yeah, a couple more words. Actually, this talk was prepared some time ago. Actually, it was prepared maybe 1 year ago. So some versions, some things might change, might have been changed since this time I prepared this presentation. However, main concept I think will be relevant anyway, just a note. And what's the purpose of this talk? Actually, in scope of this presentation, we will try to figure out how Java behaves inside the container. Are there any specifics to it? Actually, we will try to identify common Java configuration patterns and problems related to this configuration. We will try to identify key differences between Java versions in terms of memory configuration, memory control, and we'll try to understand how much memory typical Spring Boot microservice needs. Again, one note here is that I understand that everyone might understand term typical differently, right? Because projects differ from each other, projects have different technology stacks, etc. However, as I noticed, at least from my personal experience, many of the projects and many microservices in those projects do some very typical work, like CRUD operations on some entity, plus listening some event hubs, plus storing some data in database. So this is this is what I call in this presentation typical Spring Boot microservice. And again, it might differ from yours. However, again, many concepts will be relevant, I think. Let's proceed. Actually, there are a couple of slides about Java ecosystem in general. As you know, JetBrains company on annual basis prepares such reports showing distribution by some branches in each language domain. So this one I have taken specifically for Java. So you can see based on some voting in 2020, we see that for now, Java 8 is still the most popular version. Just I think it is understood why it is so, because not all projects have already been migrated to later Java versions like Java 11, or now it is even Java 17, and some legacy projects maybe just started migrating to Java 8. So there's a reason why Java 8 is still the most popular, at least it used to in 2020. Actually, one more research related to deploy options. So actually, most production projects use embedded server as a deployment option. Again, not a standalone application server, just because nowadays it becomes easier and easier and just very clear option. Actually, again, some research around frameworks. So we can see that Spring Boot is the most popular framework when in scope of Java web development. So yeah, actually the following slide shows us some typical setup when we are deploying our microservices application in the cloud. So actually, usually this is some cloud platform where we deploy each separate application as a Docker container using Java nowadays, again, Java 8 or 11. So this is a typical layered structure when we need to deploy a new microservice. So unless some specific requirements exist on your specific project. So yeah, for now, this is just to illustrate kind of main layers which are used in this specific setup. So actually, the question which might arise, do you really need to limit the memory usage of Java services? Because on some of my previous projects, we just didn't care about this. And if we started facing some troubles with memory limits like OM out of memory error, we simply increased machine memory limit, hardware limit. And in some cases, it simply solves the problem. And actually, so point is that many projects, or maybe many specific developers simply don't care about this option. And on the couple of next slides, let's see, does it really matter to explicitly control Java memory? So let's proceed. Actually, here and on a couple of other slides, I have some code samples. I will be showing you exactly the same in a second in live demo. However, on this slide, let's just pay attention at key points here. So actually, I have very simple Spring Boot-based application. As you can see, it starts with all default configurations, and actually one endpoint which it provides, this endpoint artificially triggers out-of-memory error. So in the unlimited loop, we are adding elements to this list, and at some point it fails with out-of-memory error. However, in terms of demonstration, I will explain a bit later why this demonstration is required. I covered this out-of-memory error in try-catch. So that we just can see this point when out-of-memory error happened. However, we expect the service not to fail, just because we need to track some properties of its statistics. So yeah, actually here I have an example of my Docker file. It is again very typical. I understand that for production-like application, a couple of security-related configurations would be needed in Docker file as well. However, this one is used just for demonstrating purposes, so extremely simple Docker file. So we're extending from some specific JaCoV version. We will be changing it, but this is just for example. We're locating our compiled jar file into specific location, copying it, and starting our application in a separate container. So nothing special. Actually, I have prepared one more file which is called build and run. Again, this is just for simplicity. It simply stops existing container, removes it, and builds new one, builds new image based on new application, jar application, and starts this container. Actually, I created a couple of parameters which could be optionally added here. So this script simply restarts our application based on new image. It removes previous one and creates new one. So just for simplicity purposes. Okay, so let me switch maybe between those slides, and let me switch to my IDE and show you some live examples. Okay, so let's do the following. Let's maybe start from this JaCoV version 8.191, right? So actually, yeah, maybe let me first demonstrate this demo, and then we'll be talking a bit about specific versions which I use here and why I'm using them, etc. So, okay, let's start from, again, let me demonstrate that this is the same application which I showed you on the slide. So just simple Spring Boot application having one endpoint, nothing special, Docker file, which builds our Spring Boot service based on JaCoV 8.191. And again, build and run shell script, which simply deletes container, builds new image, creates new container. So nothing special. And here is my terminal. Okay, let me clear both of them. Some preparations here. This one and this one. Okay, and now let me start our simple Spring Boot application emulating out-of-memory error. So let's build it and start. Okay, and let me enter Docker stats command in order to see some live stats of this running application. So as you can see, this container was by default limited to 1 gigabyte. Actually, this is gigabyte. I will show you these differences in a couple other slides, not now. So okay, current memory usage is about 115 megabytes, and let me call this endpoint using Kiryl command. Okay. So as you can see, I'm simply calling this endpoint, which will eventually end up with out-of-memory error. So let's see what happens in this case with the container, its memory usage, etc. So okay, we can see that we got out-of-memory error here. We can clearly see it because we are printing this error, and we can see one strange thing here. So we've got two out-of-memory error when only about 30% of memory is actually used, which is available for this container. So Java crashed with out-of-memory error, having about 60% available memory. So I understand that in this specific case, we are running those examples in Docker container. However, principle would be exactly the same when you're running it on virtual machine in the cloud, like EC2 machine in OS. So as you can see, the problem here is that free memory exists. However, we are getting out of memory error. So let's see for now how other versions, other Java versions work with this specific case. So let's decrease the version to 8.171 and do the same example. So let me restart the container. It will be created based on new image. So let me do this. Let me clean this output. Okay, let me not clean it. Let me leave it for some examples. Okay, container has been started, and let me run to Docker stats. Okay. And let's say again, so I slightly changed this Java version, and let's repeat the same exercise one more time. So as you can see, still 1 gigabyte limit, 250 megabytes limit currently in use for the service, and let me run the same command, triggering the same endpoint. Okay, let's see what happened in this case. So first of all, behavior is different. We changed just minor Java version, and we're seeing different behavior. This is strange thing already. However, let's figure out what differs from previous result. So first of all, our container was simply gets killed by Linux kernel. So there is no container anymore. And actually we see empty reply from server. That means actually this is how Kiryl represents no response from API. So that means container was simply killed by Linux kernel, and we got no response. And now let's try one final example with Java 11. Again, this version was relevant at the moment when we used it. So let's recreate our container one more time based on Java 11 and see how it works with different Java version, major version. Okay, seems I didn't exit this. Yeah, let me repeat again. Let me run new version of our container and see Docker stats for it. Okay, Docker stats. Let's see. And let me repeat this example one more time. So again, calling our OM endpoint and seeing again out of memory. And again, we see that for Java 11, about 60% of memory is available while we're getting out of memory error. So let me get back to slides for one more time. Okay. Yeah. Sorry. For some reason, refresh the index. Okay. So as I mentioned previously, here we have a clear question. We have two examples. Java versions work differently for the same situations. I mean, in the same conditions, they work differently. So what's the reason? Guys, if you have any guesses or maybe you face the same situation, so please type your guesses in the chat. And in the meantime, so yeah, let me give you maybe 15 seconds if someone wants to type something, and let me proceed then. Okay, so I think that's enough. Actually, here is the explanation based on official Oracle.com website. Guys, don't pay much attention on this texting. I will explain a couple of words, main concept here, and you will be able to read it maybe afterwards. So main point here is that by default, most of the Java versions by default take up to 1/4 of available memory on your hardware. Actually, it differs a bit for different, how should I say it, for different hardware setups. So here is mentioned that for hardware with memory up to 4 gigabytes, actually, yeah, here. So with memory of size 192 megabytes, Java will take up to half memory, and for bigger memory sizes, Java will take 1/4 of this memory. So yeah, actually, this is default Java behavior, and this is actually one of the problems. Problem is that Java takes just partial amount of memory available on your hardware, what eventually might lead to underutilization of resources, as we saw in examples with Java 11 and Java 171, right? So Java simply JVM was taking just 1/4 of available memory, and once this memory exceeds, JVM throws out of memory error, despite there is, as I said previously, 75% of available memory. This is one problem. And this is one of the guidelines mentioned by official Oracle site. So yeah, even simple program might take a lot of memory, which is not actually needed for it, just because this is default value. And actually, recommendation from again official Oracle website that you should not rely on default values of JVM memory. Okay, so let's proceed. This one is actually another example. This example shows that actually this example explains the problem related to this older version of Java 171 and why our container was simply killed when trying to acquire more memory. And actually, the reason for it is starting from actually, versions might vary slightly because I found different information in different sources. However, starting from version 8.121, Java by default does not understand that it is running inside a container. And as a base memory, it is trying to take 1/4 from your physical hardware, from your laptop. Actually, in my specific case, I have limited Docker engine itself to 24 gigabytes of memory, which can be taken. So that my application, I mean, my demo application was trying to take 1/4 of this memory, what is 6 gigabyte of memory, and it definitely exceeds container limit, which was set by Docker by default. If you remember, container limit was 1 gigabyte, and that's the reason why Docker engine decided to simply kill this container, because it was trying to acquire up to 6 gigabyte of memory. So that's a problem. And actually, for those specific Java versions where this problem exists, again, developers suggest some specific options which can enable some experimental features for the Java version and let Java version to know that it is running inside a container. However, let's talk about them a bit later. So the point is that we can learn Java to kind of learn to see how much memory is actually available for this specific JVM. However, those options are experimental; they are not recommended to use, and we will have a glance look, a quick look at them, but however a bit later. Okay, so let's recap on those problems which we've just seen. So first of all, container simply dies when trying to acquire more memory that it is actually allowed. Second point, we don't know how many containers can be safely deployed on the machine, because in this specific case, if Java starts consuming all the available memory, not seeing the limits, we cannot predict how much memory container will take, because container might be limited with some specific memory. In this case, this container will be automatically killed by Linux kernel, as we saw in our case. However, some specific container might not have a memory limit. In this case, it will grow until it takes memory available for either Docker daemon or to actual hardware, and we will end up with the same problem, but for entire Docker engine, not for one container. And actually, underutilization of resources. This is one of the problems. So you might increase your available hardware memory for your specific application. However, your underlying Java service would not consume even half of those resources. So that's the problem. So we might ask some questions to these results, like what should we do in this case? And let's proceed to our next slide. So actually, the best recommendation, again, from official Oracle website, is to explicitly limit Java memory for your services, at least for your production environment, because you might not want to play with memory settings on dev, but for production, it should be definitely enabled. So let's see which options we have in order to enable memory limitation for Java. Actually, there are a lot of different variations, different parameters. All of those parameters, actually, some Java versions have, actually, some parameters are available in all Java versions, and some of them might vary depending on Java version. So there are a couple of options suggested here. Actually, I saw all of those examples on real projects. One of the example is when you are changing max RAM fraction. Actually, this fraction defines part of memory which Java can take on your machine. So by default, this fraction is equal to 4, meaning that Java can take 1/4 from your max RAM. Yeah, this is the one option, playing with this max RAM fraction parameter. Second one is explicitly set some specific value as max JVM limit. Actually, there is one more option, starting JVM limit, starting JVM size, but we are talking currently about the kind of right limit. One more option is to actually, this option works only for Java versions up to 191. So this is required actually to fix the problem of Java not seeing actual container limits. So you may enable this option, and this option will let Java know that it is running in container, and it will look at specific file in this container specifying how much memory this container is limited with. And Java will take this as a base inside of container, but again, this option is relevant only for versions up to this one. And in combination, you can use this maximum fraction as well. Actually, two additional options were introduced starting Java 10, actually use container support and max RAM percentage. Use container support eliminates any extra flags to allow Java to understand that it is running inside a container. And instead of specifying some kind of fragmented fraction, because fraction could be 1, 2, 3, or 4, you can specify some detailed percentage of memory which Java should take from the machine. So again, if we take a look at all of those options, main difference between them, all of them, is that you might specify some fixed limit of memory, like 500 megabytes and not more, or you might specify some relative value. So actually, all of those options could be divided on relative values and specific values. So let's proceed. And actually, yeah, probably I should have asked you to guess which option, in your opinion, would be better. However, in my opinion, and based on my research, specifying fixed max memory limit is the best option compared to dynamic options to set this value. And let us elaborate a bit more on why this could be considered as the best option. So let me check the next slide. Yeah. Why this way is more kind of clear, maybe more proper way to set your hard memory limits. This is because when you're relying on your underlying hardware resources and making some relative value or relative formula calculating your available JVM memory, in this case, you are making a relation between your hardware and your application. And this relation, first of all, might not be obvious because you might not know that Java is taking only some partial memory, not all of the available memory. This might be one of the problem. Second problem is that if you have to set this relative limitation, you might not need, maybe you might not know what your actual requirements are. So for any production project, it is the best approach to test your application under high load, verify which memory it took under the peak load, and then based on this calculation specifies some fixed value. So if you are not specifying it, likely you simply don't know how much resources are required for your service, and resources could be equal to money you pay for your hardware. So it is, again, very important. So those are main kind of points why I personally consider setting specific limits as a best option here. So let's go forward. Let's proceed. Actually, we might have very expected question, like how do we determine the correct value? Because when you are running your application, you need to know how much memory is required for your JVM, because even if you specify a very low value, like, I don't know, 300 megabytes for Spring Boot microservice, in this case, it will likely start. It will still, it will still be functional. However, it will simply function not at that performance that you probably expected. So yeah, this is, so that's why we have this slide. So when we need to identify the value to limit our microservice, actually we might guess this value, as I said previously, which is not recommended, because you might end up with underutilizing or not utilizing all of your available resources, or vice versa, maybe making your service running low performance. So second option is to measure your memory consumption, and maybe not only memory, some other resources utilization under load, and use some memory calculators. Actually, I provided one of the examples from Java memory calculation. Actually, this project is available on GitHub. So afterwards, you could maybe review it, and maybe some of you will find it useful. For now, we will not spend much time on it. However, as I know, there are a couple of such projects which allow you to calculate kind of optimal memory limit for your service based on some input criteria, like on concurrency level you expect, on load level you expect, something like that. So you might search through this link and look at this calculator. So I think in our case, we will try to measure actual characteristics of our Spring Boot application, because it seems more obvious, at least to me, and the most simple. So a couple of statements about which environment we'll be using for measuring the memory consumption, and some other parameters of our microservice application. Actually, this will be, as I said previously, typical microservice application, which works with database, which receives some events from Event Hub, in our case from Kafka, which uses Gateway as an entry point, and Avrika as a service discovery. So we will be using in this example load simulator. Actually, this is Node.js-based library which allows to simulate load or your backend. I will show you configurations, which how exactly we'll be simulating this load. And again, all those links to the repository, to this simulator, to calculator, will be available in link section in the end of this talk. Okay, we will be using Java 11 image, simply because by that moment of time it would be the most popular, I would say, image type for Java 11. And as I said previously, we will be using a standard Visual VM tool for measuring metrics, not only memory. Actually, it is available in JDK distribution, at least in Oracle one, and as I remember, in AWS Coreta as well, and in some other distributions. So this is standard tool used for JDK memory management. Actually, you could use any other tool you prefer. For example, ultimate version of IntelliJ IDEA allows some profiling. However, maybe not all of the guys have ultimate version, so let me use Visual VM for this demonstration. Actually, here I have a couple of slides showing some statistics gathered from running under the load application. However, I will be demonstrating all of these in live, so maybe for now let me skip this and let me start my live session and second example. Actually, a couple of words about the configuration, about the environment again. So I have a couple of empty typical services. So we have Avrika service, which is which does actually nothing much except just some configurations typical for Avrika. So not much configurations there. We use Gateway just for simple routing, nothing special. again, just for demonstrating purposes, I will explain why we have all those kind of dependencies, why we are not running just one microservice in isolation. So we have simple gateway, simple Eureka. We have main microservice, actually, this one which we will be measuring. It provides a couple of simple endpoints. So I don't think for now it makes sense to pay much attention about what exactly they do, but I would just briefly explain. So actually, this microservice provides a couple of kind of stubs endpoints, one for actually CRUD endpoints, one for looking for microservice, second one for creating new microservice, and actually, yeah, just 2 endpoints. And we have, for running all this together, I have Docker Compose file. Actually, it starts all of the services we need. Actually, as you can see, for our microservice, we have opened 2 ports. Actually, port 3333 is required for local JMX connection. We will be connecting using JMX via Visual VM. So this is actual port service starting on, and this one is just for Visual VM connection. And those are some parameters required for Visual VM to run properly. It configures a JMX connection, JMX remote connection. Actually, we use MySQL database as an example here. We use Zookeeper Kafka, as I said, as event hub. Actually, some of items are commented here. So this is PHP admin. This is required just if you need to visually see what is located in data storage. So for my example, it is not required, so I committed it. But if your experiments you need this, you could uncomment and use it as well. So again, Eureka Gateway microservice, database MySQL, Kafka, and Zookeeper, nothing special. So let me first start all this setup. If you don't mind, for starting this Docker Compose, I will be using IntelliJ plugin, just simply because of much more user-friendly output. Otherwise, it would be not so easy to search through each service logs and looking for deployment. So it is just for simplicity purposes. Okay, sorry, I started not proper one. So we should start from a simple Docker Compose, actually this one, which starts our environment. Yeah, so let's start from it. Let it build those images. Oops, seems like some port is already located. Seems like it is still running, so let me shut it down and start again. So let's give it a couple of seconds to finish. Okay, and let me start from scratch, Docker Compose. Yeah, seems like I haven't killed my previous application. Yeah, guys, I'm sorry for taking time for it, but just my fault. Let me remove this application. Actually, it doesn't matter because it's not running. So yeah, let me, gateway didn't start, so let me restart it all. Let me move this one here. Okay, seems like our services have been started. So we have logs from each of them, database, Eureka Gateway, Kafka, microservice, and Zookeeper. Okay, so now let's go to terminal and let's, yeah, actually I have already typed this command, so let me clear it and make Docker stats. Docker stats. Actually, here we can see how much memory each of those services use when not under the load, right? So they have just started. No one calls those endpoints, and those services are not under high load. Actually, first of all, let's take that as a limit for all of those containers. We can see 24 gigabytes. Actually, as I said previously, this is limit set to Docker daemon itself. So this is common Docker limit. And actually, this memory usage depicts how much memory gets used, or actually is used right now by this specific service. So we can see that our microservice takes about 750 megabytes for running. For now, let's just have a look, and let's maybe connect to it using our Visual VM tool. So let's create a local connection to port 3333. Let's disable SSL for it, and let's connect to our locally running application. Yeah, it's connected, and let's see what we see here. Actually, as I said, we have no load on this microservice. So it uses about current heap size is 530 megabytes. So as you can see, this number is shown in bytes. Yeah, max heap size actually 1/4, as I said previously. This is about 6 gigabytes with a half. Yeah, and that's pretty much it. So for now, let's make a kind of simulation of a high load. As I said previously, I have here another Docker Compose file, which actually uses plugin artillery. As I said, it's written in Node.js, and it simply emulates a load on some specific endpoint based on the configurations. So actually here in the tests YAML file, I can specify how exactly load should happen. Actually, this configuration means that load will be increasing with arrival rate of 10, meaning that, first of all, it will be 0 simultaneous requests, then 10, then 20, then 30, and this way up to 300. So it will be increasing each second by 10 new simultaneous requests using this endpoint and this endpoint. So using this frequency, this emulator will be calling our service endpoints. So let's start this high load running our Docker Compose workload file, and let's see how our parameters change. So let's wait until it gets successfully deployed. So yeah, this one, and actually we can see artillery, which starts running. So yeah, it starts calling, starts hitting our endpoints. So let's see what happens now. Actually, yeah, let's wait a bit more, and then I will show you a screenshot of how this picture looks after after load finishes. Actually, we might wait for this. It will take maybe a couple of minutes. And let's see what changes in terms of memory usage. Actually, we can see already that CPU usage has been increased. Actually, this is pretty expectable. One more point, which is interesting here. Actually, we can see that current size of heap has not been changed, right? So it was originally about 530 megabytes. And now we can see that garbage collector just started working more frequently. So we can see that Java didn't even increase memory size for this increased load. And what has been increased definitely is threads count. As you can see, when we didn't have this load, there was about 100 live threads. However, after load has been increased, we can see that live threads count increased up to 140 live threads. So this what definitely increased under the high load, actually in this specific configuration. Besides, we can go here into thread section, and we can take a look at how many threads have been created for our service. Actually, as I said previously, it has just 2 endpoints. So if I get back to my controller, microservice controller, actually we can see that it has just 2 endpoints for creating service and fetching service by ID. And actually, it has one event listener, which simply listens for events happening in Kafka and logs them out. So, and yeah, as you understand, those controller endpoints. This one for creating microservice, it works through Kafka. So once event gets added to this template and gets sent, this event will be catched up by this listener. So I mean that those two endpoints and this listener, they all just emulate real life work of some microservice. So two endpoints and one listener here. And actually, let's get back for a second to our visual VM. Actually, as we can see, besides some main threads, we can see a lot of threads which were created simply for Kafka listeners scheduling. So we can see that Kafka listener endpoint container was created many times. There are about 20 such threads created for Kafka containers. Beside that, we have a couple of threads for Kafka liveness probes, actually Herbit threads. We can see that most of them are idle for now, not of them are working. However, those threads were created at some point, and stack size for those threads were provided as well. So, and let's see here a couple of threads used for our connection pool. Connection pool of our application server. Actually, yeah, many of them are idle at the moment. However, many of them have been created. Actually, let's get back for a second to our visual VM and let's see what it shows for monitoring. Yeah, as we can see, nothing has changed much. So under the load, just garbage collection works much faster. Our heap size, which was set by default, 530 megabytes, still hasn't changed. And the only thing we changed was live threads count. So let's get back for a second to our presentation. We will take a final look once this emulator finishes its work. But for now, let's proceed with our slides. Okay, let me one more time open it to a proper slide. Sorry, for some reason it is refreshing the count. Okay, actually, sorry guys, let me get back one more time to our visual VM and let's see one more tab which I forgot to show you. Actually, this tab is called Metaspace. Actually, we can see, as you know, Metaspace is a memory part in Java which is dedicated for loading some static meta resources about your class. About static method signatures, class names, so some meta information. Actually, we can see that metaspace size is actually the size is about 93 megabytes. Used metaspace was 90 megabytes before high load started. Once high load started, we end up with about 104 megabytes for metaspace. So actually, if we take a look, if you remember, at our container size. So if we get back to our terminal here, and if we take a look at how much memory our service uses now under high load, we can see that it is about 1 gigabyte of memory, which was taken by this container. And actually, there are a couple of conclusions which we might make based on this value, which we can see. First conclusion is that actually our kind of typical microservice took about 500 megabytes for heap, and it was enough even under high load. As you can see, once high load finishes, garbage collection starts working with much less frequency. Number of live threads has been decreased. However, as we can see, memory usage for our container remains the same for increased values. As remember, in the beginning, it was about 750. Now it is about 1 gigabyte. So memory usage increased by about 220 megabytes. So let's figure out what happens, why it increased, and which factors affect this memory increase. Why memory increased? Because as you can see, heap size was not increased. However, our containers started consuming 250 megabytes more. So let's figure out why it happened and what's the reason. And let's get back to our presentation for a second. Actually, let me not making it full screen just because for some reason it loses current slide count. So let me show you this calculation on this example. Actually, those values are quite the same as we got on our example, but it differs, I don't know, based on maybe some additional criteria. Maybe the simulator works not with the same frequency always. So yeah, we might expect slight variations here. In our case, current usage of memory for this microservice is about 1 gigabyte, but as you can see, it slowly keeps increasing. At least metaspace keeps increasing slowly, so we might expect some variations in maybe 100 megabytes. So yeah, let's proceed according to those slides. So a couple of conclusions which we can make based on this demo. So the most significantly changed part of our application was thread count. Actually, you saw that metaspace increased just slightly because some new classes have been added to memory, but it increased just one time. We saw this spike and it stopped increasing much. So now it's more or less flat. Actually, we saw that heap size did not increase, just garbage collection frequency changed. And we saw that live threads count increased. So actually, as we can see now, some value about 100 megabytes for Java heap would be enough, and even would have some gap based on this heap usage. And based on the knowledge that Java did not start increasing heap size, it just optimized itself somehow another way. So if we add maybe 200 more megabytes, it would be definitely enough for the service even under high load. So a couple of other points here. Second point is that besides heap, we have another memory part in our application. And actually, specifically for Spring Boot, it is typical to have quite a big metaspace. As you can see, it has been increased to up to about 100 megabytes. And actually, for kind of not framework-based, for some simple applications having much less dependencies, much less, I don't know, starters, some libraries, as a dependency, those applications usually require much less metaspace memory. In my experience, they for some very simple application which is not using frameworks much, it will be enough, maybe 10 megabytes of metaspace. However, for Spring Boot, it is about 100 megabytes. So when limiting your memory, just don't forget about some other pieces of memory besides heap. So if you are limiting heap with, I don't know, 600 or 700 megabytes, just beware of some other parts which are required to container if you decide to limit limit container as well. Okay, so yeah, one more point here is that explicitly limiting containers will allow you to clearly see how many containers can be safely deployed in your hardware, be it maybe your local hardware or cloud hardware. Anyway, having some clear specific limits for your Java application, you might know how you can limit your containers then, because you can simply add some operation system files to your Java application memory usage and limit your container, knowing this information. So those are main statements which we can make based on this demonstration. So actually, this slide is kind of dedicated for making a final conclusion. And actually, the conclusion for this talk would be, guys, sorry, seems I missed, yeah, sorry, wait a second, I missed one part which is related to threads. Yeah, this is essential, and let me show you this slide as well. Yeah, actually, speaking about threads, actually, as you know, in Java, we have such an option, which is called, actually, this is XSS option, this one, -XSS, which allows you to specify thread stack size. By default, it is 1 megabyte. What it actually means. Actually, as you saw on this example, we had significantly increased thread count. And can we actually measure entire memory taken for thread stacks for common thread stacks at the moment, at each given time moment. So actually, brief answer is this is not so easy, and there are no well-known tools allowing to do so. Actually, I have a link here in the presentation. I asked this question in Stack Overflow, and there is a pretty detailed answer why it's not possible to clearly see overall thread memory used by thread stacks. However, we can make a couple of guesses here. Actually, let me find this slide. Give me 1 second, please. With this slide, with thread usage. Okay, so maybe it would be this slide. So the point is the following. Actually, by default, we have 1 megabyte thread stack size. Actually, in our example, you saw that when our application was idle, we had about 100 live threads. Once load increased, we got about 140 live threads. Actually, having each thread used about 1 megabyte for each stack, we can, on the one hand, we can simply multiply stack size on live threads count. So if we had, for example, 100, we could expect that 100 megabytes would be used for thread stacks. However, each thread, when it starts, thread stack size would be granted to this thread. And once the thread finishes its work, this memory used for this thread stack will be cleared up and started being available for other threads. So that means threads consume thread stack memory only when they are running. And actually, in our example, we saw that there was about 100 running threads and under load 140 running threads. However, keeping in mind that max thread size is just max size which could be used by this thread until he gets stack trace exception. However, it doesn't mean that each thread utilizes fully 1 megabyte when it runs. So that makes it not so easy for us to calculate clear thread stack size in total. However, we may make some rough calculation, like having about 100 live threads. We might roughly assume that each thread uses its stack memory just by half, and then we might end up with 50 megabytes required for thread stack. And actually, why this point was essential? Let me get back for this slide for a second. As you can see, as I showed you in thread section, we have a lot of auxiliary stack threads. Those threads which were responsible for some listening some Kafka events, or listening maybe some making some liveness probe for Kafka. Some threads which are required for application server, some threads which are required to making some live checks in database, and you end up with so many live threads, even in the application, which is not doing much multi-threading work itself. I mean, no multi-threading work inside our endpoints. So even in this very simplified application, we have about 100 live threads just because those threads are required for some auxiliary work, even despite they are not busy at some time and they are idle for now. However, at some point when they were running, they were taken with thread stack size, and that what also consumes our memory. So again, when you are limiting your memory, just keep in mind that your application might require up to maybe 100 or 150 megabytes just for stack size for thread stack totally, and it might require up to, I don't know, 150 megabytes, especially for Spring Boot, which is having a lot of dependencies. It might require 150 megabytes for Metaspace as well. So why I mentioned those components on this slide is because actually those components, they most significantly affect Metaspace and stack size because of those reasons which I have already mentioned. That some applications might require additional auxiliary threads to be started just for some live checks, some additional work which could be done in the background. However, they require memory. actually a lot of dependencies, which is what is maybe the mostly actual for Spring Boot application, which usually uses a lot of dependencies, a lot of status, a lot of libraries, I don't know, some common libraries, and as a result, we end up with quite a big metaspace size for Spring Boot applications. So those are 2 points which you need to consider when you are making kind of typical microservice. You need some memory for heap, and you need to figure out how this memory utilization changes under the load. Then you need to figure out how many threads available in your application, and maybe if you decide to decrease this threads number, you could consider some other solution like reactive programming with some reactive application servers having less threads for serving the client requests. However, when you are making your memory limit, you need to keep in mind that besides heap itself, you have some other memory pieces requiring you to make this limit not quite equal to your max heap size. Otherwise, you would end up with change it, or maybe not kind of, let me say it this way. As I said previously, your Spring Boot application might start even with 300 heap size. However, it would perform not as you likely expect. So if you are limiting your heap with some value which is equal to current heap size, you will end up with heap decreasing just because Java will take some memory for metaspace and for threads. So this is essential, and just keep it in mind when limiting your memory. Okay. So as I said in this example, we have calculated how much memory is required for heap, how much memory is required for threads, how much memory is required for metaspace. Also take in mind that when you are building your container, your jar inside of this container will also consume some memory. And finally, for this very simplified application, we got something about, actually, this is from my previous run when I was preparing this presentation. And actually, for our current run, we can see that our microservice, after high load, ended up with something just a bit above 1 gigabyte of memory required for it. So this is actual memory, which is in usage by this container. So if you limit this container with some value like 1 gigabyte, 100 megabytes, likely it would be enough for such kind of services, even under high load. So let's get back for the presentation, and maybe actually, all those things which I described in voice are presented on the slides as well, so that you can repeat all those steps I made in my demo. And yeah, so let me get back to one of my last slides with conclusions. And I understand that saying here some very specific conclusions, like I don't know, use only reactive stacks always, or maybe I don't know, use only those components, or don't use many dependencies. Those things like don't make any sense, just because each project has its very specific, and each service might be deployed by different ways with different configurations, etc. However, as we saw in these examples in this demo, Java might have different default behavior based on its version. And despite we are moving towards Java 17 already, some projects might still use Java 7 version, Java 8 version. And as I said previously, there are a lot of differences between minor Java versions, especially in Java 8 maybe. So just beware of those differences and know your Java version and how to properly limit its memory, specifically in this Java version. Or maybe simply update your Java version if it has some vulnerabilities or some problems with default behavior or memory management in general, maybe not default behavior. Okay, second conclusion is that the best practice is to explicitly limit not only Java, but containers as well. This principle would allow you to clearly see how many containers you could deploy on one hardware, on one physical machine in the cloud. Actually, on one virtual machine, but I mean on one machine. Otherwise, your containers might simply consume all the available memory, and you might end up with some situations as I showed you in one of the first demos. So limit not only Java, but also container in which it is running. And actually, third conclusion is that Java memory is not only about heap. So when you're identifying how much memory your Java application needs to be limited with and how much memory you need to specify for a container, just keep in mind that besides heap value under the load, you need to consider stack and metaspace sizes. And for some applications, especially framework-based, those stack and metaspace sizes might require maybe up to 300 megabytes. So they are not quite big, but still need to be taken into consideration. So just keep it in mind. Okay, actually, guys, that's it from my side. So please ask your questions in the chat, or maybe you can contact me via email presented on the screen. Also, I would note that my colleague Pavel helped me with creating this content. So just maybe you can contact him with some questions, but as a primary point of contact, please consider myself and contact me. Here we have a list of resources used for this presentation, actually a couple of articles which might be useful in understanding different Java version specifics, and two repositories links, because two different repos have been used for this presentation. Actually link to calculator and to specifics of measuring thread stake life memory. So yeah, you can find all required materials right here. And thank you everyone for your attention. And again, please ask your questions in the chat or contact me via email if you need to. Thank you, guys.
Yeah, thanks, Kiryl. And yeah, actually, there are already a couple of questions, and one of them, I think it was kind of guess about why container consume a lot of memory. It
Yeah,
was a
sure.
question: cannot claim your memory space fast enough. Yes, I guess you already answered it during the presentation, because it was really in the really beginning of your presentation. And the second question, to what is the name of Docker Compose plugin that you use in your idea?
Okay, yeah, maybe let me answer this. Guys, as I remember, this is just Docker plugin. This is not plugin for Docker Compose. This is Docker plugin. And actually, if I'm not mistaken, it is built in even in community idea version. So let me check if I'm not mistaken. Yeah. So, guys, this is just bundled. Мы на русском сейчас или нет? Я немножко...
Yeah, we are trying to speak in English. Yes,
Sure.
we are
Yeah.
continuing in English. Yeah.
Yeah. Sorry, guys. Yeah, sure. So as I said, this is bundled plugin. I don't remember whether it is bundled in community version because I'm using ultimate version, but if I'm not mistaken, yes. So I definitely remember that community version does not support Kubernetes plugin out of the box, but Docker should be available there. So simply go to services tab and you will see Docker here. However, before that, you need to configure Docker in the, to which host Docker needs to connect when it starts. So you can configure here all the configurations like Docker registry and some other stuff. So again, this is bundled, just try to look for it in settings.
Okay, thank you, Kiryl. And the question about, will this presentation be available later? Yes, it will.
Yeah, sure, I will send.
Okay, any other question, guys? Yes. Is there any difference between Oracle and AWS current Java instances? I mean, memory consumption, thread, and etc.
Actually, I didn't compare those versions in this specific context. So I didn't compare memory usage and I didn't profile actually Amazon Corret, unfortunately. However, this is in my plans. So maybe next time I will show you, maybe I will answer this question in more details. For now, I cannot do that, unfortunately.
Okay. And if there is no more questions, I'm going to say thank you, Kiryl, again, and thank you all of you guys for your attendance. I hope it was interesting for you and useful, because it was really deep dive in memory allocation from Java and containers perspective. Really cool. Thanks.
Thank you, guys.
Yeah, and bye bye.
Bye bye.
Have a nice day, evening. Bye.